turn on the microphone.
It's fine. Yep. Can you hear me? So,
they can only hear you.
Yeah. Okay. Yeah. So again, pleasure to be here at this special workshop. I will talk about merging black holes in an astrophysical setting and focusing on the massive black holes. So most of the talks I've heard have pictures of black holes like this, and I'm an astrophysicist, so the picture we are dealing with is more like this. But don't be too alarmed, I will try to keep things simple. Hopefully the audience here will get something out of this talk. So I want to do three things. I want to give an introduction first and motivate the presence of gas around two black holes. And give you some background why we think the gas should be there and why you would care about the presence of gas. Gas, by the way, I discovered in, we call it gas, but usually it's called matter in this kind of audience. The theoretical part of this talk will essentially be considering the problem of two-point masses interacting with a gaseous disk and how that affects the electromagnetic luminosity and the in-spiral of the black holes. And then the third part would be observations. I want to present some candidates for in-spiraling black holes pulled out of just quasar surveys, and then discuss, this might be the most interesting part for this audience, the connection to gravitational wave sources. Now, this is an audience I want to actually tell something I learned after I moved to New York about how the word black hole was invented. So this is the picture from my office in New York City. And when I walk sorry? It's all yours? It's from my window, yeah, looking downtown. There's the Empire State Building. But when I walk to work, I walk past this building every day. This is on Broadway, and you probably, some of you recognize this building. Can you raise your hand if you recognize this? So people don't watch Seinfeld, I guess. There are lots of tourists taking pictures of this building because this is the opening episode of Seinfeld. Europeans might recognize this from the Susan Vega song Tom's Diner, which is actually composed about this place. So it's already famous for two things. But in fact, this building, these windows here, constitute the Goddard Institute for Space Studies. It's a NASA center associated with Columbia on 112th Street and Broadway. Columbia is on 116th and Broadway. This is John Wheeler, who I think if I ask you who coined the word black hole, most of you would have said John Wheeler. But I read his autobiography a couple of years ago, and this is what he said there. In 1967, Vittorio Canuto, head of NASA's GISS Institute at 2880 Broadway, invited me to a conference. And he said we should, at that talk he gave there, he argued we should consider the possibility that at the center of a pulsar is a gravitationally completely collapsed object. I remarked that one couldn't keep saying this long word, gravitationally completely collapsed objects, over and over. One needed a shorter phrase. So how about a black hole? Asked somebody in the audience. I had been searching for just the right term for months, mulling it over bed, in the bathtub, etc. So I was rather amused by this, that I walked past this building, which is so famous, there are tourists there, and in fact, is, according to Wheeler, is the birthplace of this term we all use. By the way, it's worth reading because the next page he goes over how the analogy to the black body radiation is what made him really like this term. Something that absorbs light and is already a very popular term. Okay, so with that cleared up, I want to move on to the scientific part. As I said, most of the talks we heard have to do with picture of emerging black hole like this. Pure distortions in the space-time metric. Now, of course, for a merger to happen like this, the gravitational radiation actually has to take the black holes from some large separation and drive them to one another by the release of energy through gravitation waves. Now this process actually takes quite some time and depends on how large is your separation. As you know, in astronomy, we've discovered there are two types of black holes, stellar mass black holes in the range of 10 to 100 solar masses. And then we have supermassive black holes from millions to billions of solar masses. Now, if you want the in-spiral to take less than the age of the universe, which we know to be 10 to the 10 years, you should start from 0.1 AU for a stellar mass binary or 0.1 parsec for a billion solar mass binary. These numbers are actually not unnaturally small. So stars or stellar remnants generally are much farther apart than 0.1 AU. And supermassive black holes in the nuclei of galaxies, as I'll argue, are much farther than 0.1 parsec. So you guys, or if you want to merge black holes, some astrophysics has to happen there to bring them closer in. Now, luckily, so the rest of this talk will mostly be about supermassive black holes. In the LIGO context, it's not clear if there will be gas at the last stages of the merger. So I want to focus here on the massive black holes, where I think this is actually extremely well motivated, because we think we know how the supermassive binary black holes are produced. We have pictures of galaxies. First of all, we know that in the nucleus of every galaxy, that we could tell whether or not there is a massive black hole. We find one from the observations of about 100 nearby galaxies. And then we also see galaxies, they merge. So these are two galaxies with the Hubble Space Telescope. They made a pass by one another, and they had made these tidal distortions. And this happens quite frequently. So you can go through the argument like this. So first of all, most galaxies contain black holes, as I said. And in a lifetime of a galaxy, there's typically several major mergers. So you expect pairs of black holes to be produced in the nuclei. Now, the same mergers which place the black holes in the center of a newly born galaxy are also known very well, theoretically and observationally, to drive the gas into the center of the galaxy to tidal interactions and torques. This is well understood, and starbursts are observed in quasar nuclei. So this happens. Most galaxies have gas. I just don't want to details, but this kind of black holes, so 10 to the 7 or less black holes, live in gas-rich disk-shaped galaxies, spiral galaxies. Bigger black holes live in so-called dry elliptical galaxies, which don't have obvious gas, but they still have enough gas that is comparable or larger than the mass of the black hole. And so a natural outcome of this process, a pair of supermassive black holes in the middle of the new galaxy with the gas that's been funneled in. The gas actually cools, deflates its pressure in the direction perpendicular to the rotation and forms a disk. And so the natural outcome of this is a quasar, a gaseous disk enveloping the binary black hole. Now, in fact, we cannot resolve this thing directly in electromagnetic observations, but the one-slide summary of the status of directly seeing this is here. So this is a poster child X-ray observation where there's two active massive black holes in the middle. They're separated by a kiloparsec. We can't actually resolve the 0.1 parsec where we are safely in the gravitational wave regime. This is 10,000 times farther. The best we can actually do is in the radio, where there's interferometry, resolution is better. So the winner is a 7 parsec separation radio galaxy with 2 active radio cores. That's the closest we've actually seen. That's still about a factor of 70, too large to actually merge in a Hubble time. Now, however, as I'll argue, the gas disk that is formed there can help you with this. One last slide, again, particularly for this audience, why you should care about the photons that might be generated from the matter around this binary. So, as you know, just by looking at gravitational waves, you can learn a lot about the general relativity and the gravity on short scales. There are 3 kinds of regimes where 3 different instruments can detect these gravitational waves. LIGO, which we already heard about. LISA will be sensitive to bigger mass black holes in space. Pulsar timing arrays probe the lowest frequencies, highest mass black holes. Now, for us astronomers, this will be a revolution to see photons and gravitational waves at the same time, simply because we study accretion. Here we would have a situation where we know the masses of the black holes, their spins, their orbital parameters, and we could study the outgoing light and spectrum and time variability. So that's just a treasure trove of stuff for accretion physics. For LIGO sources, it's turning out to be a treasure trove for basically studying massive star formation and stellar evolution and how you form actually a binary. In the context of big black holes, we know quasars and galaxies evolve over cosmic times in unison. They fall and rise in populations. So it would be great to understand photons which come out of quasars and then seeing mergers of black holes in parallel. Now for this audience, I think it's also very interesting. You probably are familiar with all this, but let me just repeat. So the standard cosmological test based on the supernova, which I missed yesterday, but I believe you heard a talk about supernova Hubble diagrams. In principle, if you have an electromagnetic counterpart of a gravitational wave source, you can repeat the same kind of exercise because you measure the distance to the source from the gravitational waves. You won't know the redshift, but if you have an electromagnetic counterpart, you can measure the redshift and do the same exercise. So that's for general cosmology maybe less exciting these days because we already know the cosmology better from supernovae and CMB and cosmic microwave background and other large-scale probes. But one particular to compare the Hubble diagram you get from gravity waves and from the supernovae, because one is based on photon propagation, the other is based on graviton propagation. They would not agree in the case of extra dimensions or some modifications to gravity on large scales. Now, we also proposed a while ago that you can actually look at the time of arrival of the photons and the gravitons. If their speeds are not equal, if one of them differs from the speed of light, then they arrive at the same time. So you can learn about massive gravitons, for example, this way. Or again, extra dimensions. And in fact, if you have a massive graviton, the energy of the graviton is going to depend on frequency, so the velocity difference. So gamma factor will depend on the frequency. So if you have several frequencies in gravitational waves, this time delay should depend on the frequency in a way that's predicted by this formula. So gamma will depend on frequency. And that assumes Lorentz invariance. So if you can actually test the time delay as a function of frequency, you can even test Lorentz invariance. And of inside, it's great to have the photons because it can actually help you with the gravitational wave detection itself. A low signal to noise source might be more convincing if you have the photons from it. Okay, so the second part of this talk will be now about modeling this process. So, as I said, we expect gas disk to form around the binary. Now, for a single black hole, supermassive black hole in the galactic nucleus, we have a very good working picture of how this happens. Quasars operate by having an accretion disk. It's not fully understood how this is fed, but for our purposes, there's a thin, stable, geometrically thin, optically thick disk of gas, which is got viscosity, so it's accreting on the black hole and it's producing dissipation and photons. So our problem here is actually very simple. We just want to, the simplest way to model this is to put a second black hole in this picture. So you have a gaseous accretion disk and you put a second point mass. So this is actually very well posed. Maybe I will skip. But let me just say, so again, very well posed problem. 2 point masses with a gas disk. And they're really, again, you should really care about this for figuring out how much gas is actually reaching and accreting on the black holes for a binary. That is important for setting the total luminosity of the object. Now, most of the luminosity is coming from tens or 100 Schwarzschild radii, so you want gas to reach there. You want to know if the gas actually impacts the orbital parameters of the binary, because we want to actually shrink the orbit and make sure the merger happens once gravitational waves take over. And then you can also worry whether the gravitational waveforms are actually impacted by the gas. So I only have one slide on these details because I think probably you don't care too much about details of this simulation. I just want to emphasize this is a very simple simulation. It has only gas dynamics in 2 dimensions. It's it's a very well posed problem, basically 2 point masses and gas initially on Keplerian orbits. So just hydrodynamics in 2 dimensions. We use this code called DISCO to follow this system. It's 2D Newtonian hydrodynamics. So this would be the relevant case when, let's say, the black holes are separated by 100 Schwarzschild radii or more. So certainly at a parsec it would be relevant, or 0.01 parsec even. The gas can cool and heat, shocks, it can shock. The black holes are on the grid, simulation grid, so they can accrete. We run these kind of simulations for thousands of orbits, so we have a very nice pattern which is quasi-steady state, so we know how the system behaves. And we can study the morphology of the gas and the fueling rate, etc. Now, so I'm going to skip this slide and just show you the movie because it summarizes everything I want to convey. So this is the surface density of the disk, which was initially a smooth accretion disk, except we put in these two black holes, which rotate on a circular orbit at a prescribed rate. And so, as you can see, the most conspicuous feature here is that there's a large cavity in the middle. This was actually known before because if you have a rotating 2 masses and you put test masses around here, there are no stable orbits. Those particles get torqued and flung out. So this tends to do that. But you can see that actually this cavity is a very low density, but you see that gas is actually flowing in. There are directions where angular momentum is removed from the gas and it falls in and accretes on the black holes. And this accretion is very good because it can actually produce luminosity. You can also see that this is a very distorted shape with some spiral arm features, and that can help promote the merger, I'll say in a second. Finally, you could also see, if we play the movie again, that this accretion is episodic. Sometimes the black holes are fueled, sometimes they're quiet. So this is a summary of the most important thing you can extract from this kind of simulation is the accretion rates. So this is a case where the mass ratio is almost 1 to 10, typical expected in a merging galaxy. And this panel here shows as a function of orbit, so from 400 to 425 orbits, it shows you the rate of accretion onto the lower mass black hole in green and the more massive black hole in blue. So what you see here is that the lower mass black hole is accreting. This is in units of the rate of accretion for a single black hole with the same mass. So what you see here is the lower mass black hole is basically fueled at a rate that's actually even higher than a single black hole would have been fueled, and is periodic, tracking the orbit, and fluctuating by 50% order unity. So these are the takeaway points here. This binary is very efficient in expelling gas and creating a cavity. It's completely inefficient in stopping the accretion and creating a bright quasar-like source. Moreover, the accretion fluctuates on the orbital timescale, so the very, very telltale signature. And it's also important that it's the lower mass black hole that's accreting, because that black hole is actually moving faster than the heavier black hole, and that will be important in a second. So finally, the torques. It's basically this gas disk that I showed you here. Let me just go back to the picture. This affects the orbit of the black holes basically for two reasons. One is that you're directly accreting mass and momentum, so you're changing the orbital parameters as you're growing the black holes and pushing them, endowing momentum. Also, there's gravitational torques. This gas is not symmetrically oriented around the black holes, so they have direct gravitational torques. And so we measured this, and maybe again I just get to the punchline. So the gravitational torques turn out to dominate. This is the surface density, time averaged over many orbits. And this is the torque surface density. So there are two black holes here, they're moving around this way. The gas that's behind the black hole in blue shows negative torques, it's pulling the black hole backwards. The gas ahead of the black hole is pulling it forward. And the net effect turns out to be that the angular momentum is actually extracted from the binary and given back to the disk. This I think is very counterintuitive because the gas that's rotating out here has much higher specific angular momentum than the point masses. But it just turns out you can actually see that in the movie. There's a slingshot kind of mechanism effect where you actually flip the gas back out. So the gas shocks, approaches the black holes, it's slingshotted back out with a larger angular momentum it had before. So angular momentum is continuously taken out of the binary and put into the disk. And the disk transports it out with enhanced viscosity. So this, now we understand this quite well. And the time scale for orbital decay, for example, if you pick an orbital period of 1 year, it turns out to be independent of mass of the black hole. If you say the black hole is accreting at 30% of its fiducial so-called Eddington accretion rate, which we think is typical of quasars. So in a few million years, this binary would merge due to the disk. And just for comparison, if you go to the time in the separation when the orbit is a year, if this black hole is a very massive pulsar timing kind of 10 to the 9 solar mass black hole binary, the gravitational wave emission would cause it to spiral in 10 to the 5 years. So this is a significant perturbation to the gravitational wave in spiral. For a LISA type of black hole, million solar masses, the in spiral due to gravitational wave would be 10 to the 10 years. So this is a very small effect, but it can help you get to that point because it only takes 1 million years. So it's a way to produce the LISA events. Now I'm gonna, I have only 5 minutes, so I'm gonna skip this and go to the last point, which is about observations. So first is that we did the obvious thing after we discovered this periodicity and went to catalogs of quasars. And there are actually catalogs of quasars, about 300,000 quasars, which have time series data over about 10 years. And you can actually look for periodic variability. So we and another group at Caltech have recently done this, and the upshot is that the Caltech people looked at 250,000 quasars. They found 100 candidates, which are periodic. We looked in another survey, so-called Palomar Transient Factory, which had 36,000 quasars, which goes somewhat fainter, but smaller area, and we found 33 candidates. So we have 150 quasars now, which look periodic, and they're candidates for being such binaries. So the last, and they look like this. I'm gonna try to go fast because I want to go to my last point, which is, in fact, periodic variability, even if you didn't have the hydrodynamical fluctuations, would be inevitable due to relativistic effects. So you have two black holes, and they're accreting, and they're in orbit. So this is a very simple point. If the black hole is moving at a significant fraction of the speed of light, when it's bright, it's a moving light bulb, so it cannot be seen stationary on the sky. It will, at the very least, will be Doppler shifted, and the Doppler boost is of order V over C. So once the separation is such that the velocities are a few percent of speed of light, you're going to see few percent variability sinusoidally on the sky. And in fact, for one of the quasars, we showed that this is a very good explanation. But I want to, this will be the, I think I'm getting out of time. So this will be my last slide. I think it's very exciting that this is practically inevitable in the LISA band. So this is a diagram which you can ignore all the curves except look at this one, the middle one I marked here. This is the LISA noise curve. This is the orbital frequency. And this is the track of a binary which is 10 to the 6 solar masses. So what happens is it enters the LISA band. From this point, it's visible to LISA when the frequency is about a few times 10 minus 5 hertz. It takes about 5 years to get to here. And that's a monumental milestone in the history of this event, because about a month before the merger, you already can localize on the sky where this source is. This is something we showed a while ago. It's a signal-to-noise calculation, parameter estimation calculation, but you only use the data stream from here to here. And you can tell on the sky to about 10 square degrees where this event is. And you go up to about a day before the merger. You're still in this mildly relativistic regime, and you still safely have these disks around the black holes. They haven't been destroyed by the merger. And so you inevitably have an electromagnetic chirp which accompanies the gravitation wave chirp. You will have the same exact phase. The only difference, and you accumulate about 300 cycles during this time. So you can compare the gravitation wave chirp to the electromagnetic photon chirp. And that tells you basically I think I'm going to skip this because I'm out of time. It just tells you a constraint on any speed difference between gravitons and photons. So actually my secret hope is that somebody will be now very excited and say why it would be useful if we measured the difference to about 10 minus 17 or so, fractionally. So I think I'll just put up my conclusions and stop. Thanks.